Okay, so for example, what we were doing earlier in the chapter was we were integrating f of x to find the general function and use the initial condition to determine the constant of integration. So there's another way that you can find use the initial condition to help you solve these particular problems. That is, take your initial condition y of 0, add it to x sub 0 to x of f of t dt. So for example, taking a look at 1a, I'm giving you the derivative of cosine x. I'm giving you the initial condition y of 0 is equal to 1. So what we were doing before is I would integrate cosine x, and I would have to write what? I'd have to write the plus c, and then I'd plug in the 0 for x and set it equal to y, and then I would solve for c. So another way I could do this particular initial value problem is, remember, dy over dx is a change in y over change in x. So you can isolate dy, treat this just like a fraction. I can multiply both sides by dx and write dy is equal to cosine of x dx. Then I can integrate both sides of the equation. Well, I know when I integrate dy, that's just a y, equals. I have now my initial condition, which is given to me as y of 0 is equal to 1. So I can take my y of 0, add it to a definite interval. Now the thing is, this initial condition is starting when t is equal to 0. So you always want to make sure that this lower bound matches the same exact x value as what's given to you in the initial condition. And when we get to accumulation problems, yes, there are two ways to solve this problem, but when we get to accumulation next week, this is very critical. You're going to have to set these initial value problems up this way, just like you had to do in that last FRQ. And again, I'm just going to call this an uppercase X, just to distinguish my variables. So now, to solve this particular problem, I have y is equal to, what is y of 0? Y of 0 is equal to what? 1 plus the antiderivative of cosine x is going to be a what? Sine x. And again, I'm going to evaluate this from 0 to uppercase x. So y is going to be equal to 1 plus, plug in your upper bound and lower bound, sine x minus sine 0. So then y is just going to be equal to 1 plus sine x. Had I used my indefinite interval, had I just integrated cosine x and used sine x and got that and wrote the plus c, plugged in the 0 for x and y for 1, you'll get the same exact answer. It's just another way to handle those initial value problems. So any questions on that one? Yes? There's problems where it'll be easier to do it this way. But I guess when we get to accumulation next week, you'll want to be able to do it this way. Taking a look at B, dy dx is equal to x plus 1 divided by square root of x. And again, they're telling you the initial condition, y of 1 is equal to 0. First of all, how am I going to integrate this fraction? This is a good review. Divide it out, exactly. So you have to split up this fraction. So dy is going to be equal to x over x to the 1/2 plus 1 over x to the 1/2, all times your dx. Now before I integrate, let me simplify x divided by x to the 1/2. So x divided by x to the 1/2 is just then x to the 1/2. And I can rewrite 1 over x to the 1/2 as x to the negative 1/2. So now I'm ready to go ahead and start integrating. I know the integral of dy is just a y, equals. So now I'm going to take my initial condition, which is, again, y of 1, plus. Now this is where you have to be careful. The lower bound of this integral is not going to be 0, but it's going to be a 1 to x of x to the 1/2 plus x to the negative 1/2, dx. So just remember, whatever this x value is, that's got to be the same value as the lower bound. Notice this one's not starting at 0. So then y is equal to, again, they're telling you y of 1 is equal to 0. Plus, boy, we had an interesting time trying to do the derivatives last class of this one. We had to go back over power rule for derivatives. What is the antiderivative of x to the 1/2? 2/3 x to the 3/2. Plus, what is the antiderivative of x to the negative 1/2? 2x to the 1/2. And again, I need to evaluate this from uppercase x to 1. So then y is going to be equal to 2/3 x to the 3/2 plus 2x to the 1/2. Now remember, your lower bound is not a 0. So minus. Make sure you open up a set of parentheses, and I want to plug a 1 in. So 2/3 times 1 is just 2/3. 2 times 1 to the 1/2 is just a 2. What is 2/3 plus 2? 8/3. So it's going to be, my final answer then is going to be y is equal to 2/3 x to the 3/2 plus 2x to the 1/2. And again, this is going to give me 8/3, but it's following that subtraction sign, so it's minus 8/3. Okay. So any questions, guys, on how we handle the initial value problems? And again, this is with definite integrals versus what we did earlier in the chapter where we had the plus c, where you were dealing with the indefinite integrals. Okay, last part of this is going back over the fundamental theorem of calculus part 2. And remember, with the fundamental theorem of calculus part 2, we looked at what happened when your bounds was a variable, when your upper bound was that variable x. Well, you also could possibly be looking at limits of integration other than x. So to find the derivative, you're applying the chain rule. So what's happening is, instead of one of your bounds being an x, it could be some other function. Or it could be that both bounds are a variable expression. So basically what you have to do, again, when you take a look at the derivative of the antiderivative, we talked about how they are inverse operations, are going to cancel each other out. But now notice what happens. With this upper bound, what you're going to have to do, after you plug g of x into your function, you end up multiplying by the derivative. So you have to take the derivative of the bound and multiply it. It is also possible for both limits of integration to be a function. You're still going to apply the rule of taking the upper bound, plugging it into the antiderivative, and again, notice you're going to be multiplying by the derivative of the upper bound. But notice the lower bound is also a function, not a constant. So you still apply your fundamental theorem of calculus, where you're going to subtract the lower bound, and notice you also have to multiply by the derivative of the lower bound. So let's take a look at some examples. So notice they're still asking you to find the derivative of the antiderivative. Notice my lower bound is a constant, which is what I want. But notice my upper bound is an x squared. So what I'm simply going to do is I'm going to plug in my x squared for t, so the square root of x squared plus 1. But then I have to multiply by the derivative of x squared. And what is the derivative of x squared? 2x. And you're done. Remember, you could do this the long way, like I showed you when we were going over the fundamental theorem of calculus and why this works. Yes, you could integrate. You could go ahead and find the antiderivative of square root of t plus 1, plug in your upper bound minus the lower bound. Then you could take the derivative of that answer that you got, and you'll get the same exact thing as what we just did. That's the proof as to why this works. What's the problem with b before I get started? What's the upper bound is a what? Constant. So the lower bound has my variable expression in it. So first thing I want to do is I want to negate this. So I'll rewrite this as my bounds from pi to 1 over x, sine of t dt. So now, taking the derivative of the antiderivative, I'm going to plug in my upper bound for t, which is a 1 over x, times, what's the derivative of 1 over x? Negative 1 over x squared. Because remember, 1 over x is actually x to the negative first. So remember, when you use your power rule, that's negative x to the negative second. If you wanted to clean this up a little bit, you have a negative times a negative, which is positive, so you could also write this as a sine of 1 over x, all divided by x squared. Any questions on B? Now let's take a look at part C. Notice part C, both your upper bound and lower bound have your variable expressions. So negating to get the lower bound to be a constant is not going to work. So this is where you simply plug in your upper bound for t, so x squared minus 1 over x squared squared plus 1. And I need to multiply by the derivative of the upper bound. And what is the derivative of the upper bound? 2x. Minus. Now I plug in my lower bound. So I'm going to take 3x and plug it in for t, so 3x minus 1 over 3x to the second plus 1 times the derivative of the lower bound. And the derivative of the lower bound is just a 3. And again, if it's free response, you don't need to distribute. You don't need to do anything. Just leave it alone. So any questions on how, again, this only applies when you're taking the derivative of the antiderivative. So any questions on that one? So let's take a look now. Notice your antiderivative is defined as this particular function. Like we talked about the other day when we were doing those FRQs, and especially with the graph FRQ, always know the relationship between what the antiderivative is named as versus the function inside. What is the relationship between f to the function inside the antiderivative? What is the square root of 3t squared plus 1? That is your what? What is that? That is my f prime. Make sure you always remember that relationship. Establish it, whether they're giving you a graph or they're giving you just a function. So now how are you going to find f of 2? You're simply going to take 2 and plug it in wherever you see an x. So I'm going from 2 to 2, square root of 3t squared plus 1 dt. What's that going to be? 0. Why? The bounds are the same. Yep. F prime of 2. Well, remember, f prime of x we've identified from the integral. F prime of x is just equal to the square root of 3x squared plus 1. So then how do I find f prime of 2? I'm simply going to do what? Plug in a what? 2. So square root of 3 times 2 squared plus 1 is going to give me square root of 13. So whether these problems are given to you as graphs, whether they're given to you as functions, just make sure you always understand the relationship of the function inside your integral versus what the antiderivative is defined as. So now how are we going to find f double prime of 2? Right, so since I know f prime of x is equal to, and I'm going to change this to a fractional exponent. What am I going to have to do with f prime? I'm going to have to find the second derivative. What rule am I going to have to use to find this derivative? Chain rule. So 1/2 times 3x squared plus 1, what's that new exponent going to be? Negative 1/2 times what? 6x. So I can clean this up because 1/2 times 6 will give me a 3x on the top over 3x squared plus 1 to the positive 1/2 when I move it to the denominator. So now that I know my second derivative, I can plug a 2 into my second derivative. So 3 times 2 is 6 over 3 times 2 squared plus 1 to the 1/2. So what's that going to be on the denominator? That'll be a square root of 13. Don't worry about rationalizing, guys. You don't have to worry about rationalizing denominators. The only time you have to worry about rationalizing